So welcome back to lecture 19. This is part 2, and kind of the goal in this part, the first goal in this part is to kind of prove this theorem here. So kind of you want to pay attention to is like what we're doing is we're kind of carving up our vector space into these subspaces. Now they have an overlap because they're subspaces, they all contain 0, but other than that, they're actually going to have no particular overlap. So what we want to show is that we actually have a direct sum of the subspaces. Okay, so let's prove that. Okay. Oh, and let me actually point out that the dimension result will actually now follow from the first result, because what is the dimension of the subspace? Well, because it's a direct sum, it's the dimension of each of the individual parts. So the dimension, the sum of the dimensions has to be less than or equal to the dimension of V. So we won't prove that. Really, the only part we're going to prove is going to prove the direct sum statement. So remember how you do this is you want to show something's a direct sum, and you want to show that anytime you can sum up to 0, each of the individual elements have to be 0. So let's say we have u1 plus u2 up to um being equal to 0. Now what we know is that each ui is an eigenvector of lambda I. Okay, so i.e., how does ui get inside of this space? It satisfies the property that when you evaluate t at ui, it's the same thing as multiplying ui by lambda I. Right? Now, so each of these guys are eigenvectors, and we know that eigenvectors from distinct eigenvalues are linearly independent. So I'll write that out. So since eigenvectors from distinct eigenvalues are linearly independent, this is a property that we proved in a previous lecture, then we have that each ui has to be equal to 0. And that's actually all that we need to show in order to say that we have a direct sum of these subspaces. Okay, so here is the definition that we're really interested in. We say that an operator is diagonalizable if there's a basis of V such that the matrix associated to the operator T with respect to this basis is a diagonal matrix. So with respect to this basis. Right? So if we go back to our original question, right, what kind of our motivation, right, is can we do better? And what we want to do is when can we know that the operator T is a diagonal matrix? That's in some sense a better answer than the first statement. Okay, so the question is now becomes when can we decide whether an operator is diagonalizable? Now notice that this is just a definition. That's what we would like. We don't actually know that we can do it yet. Now, yes, but if you think back to 1b, we were using this term diagonalization. And in fact, what we were doing is in Math 1b03 was actually cooking up a basis to create a diagonal matrix, but we didn't express it that way. So let me try to tie some of these pieces together. Right? So consider the linear operator in R2 given by taking the pair xy and mapping it to 7x plus 2y. Right? And so if you want to think back to kind of what we're doing in kind of in Math 1b language, so I'll put it over here, 1b03 language. What we were doing was we're taking the matrix 7 minus 4 and 2, 1. Right? So this is, we're looking at this particular matrix, and what we want to do is kind of break apart this particular matrix, right? We want to write it as some invertible matrix times a diagonal matrix times the inverse of the first matrix, right? So in fact, you know, if you use the standard basis, you actually get precisely this matrix right here, 7 minus 4, 2, and 1. Okay, so this matrix here clearly is not a diagonal matrix. It's not even upper triangular matrix. Now, you may want to go back and kind of review how you found the diagonalization of a matrix, and I'll try to kind of quickly run through it with this example. So the first thing that you needed to do is take your matrix and you needed to find the eigenvalues, and I just will tell you what they are in this case, right? So the eigenvalues for this matrix are 5 and 3, and you find this by doing the characteristic equation. And then what you needed to do is for each of these eigenvalues, you needed to find the eigenvector. Okay, so you take the matrix and you subtract 5 minus the identity matrix, because we're going to look at the eigenvector for lambda equals 5. So hopefully this is all review. And you get the matrix 2, 2, minus 4, minus 4. And you row reduce it to get the matrix 1, 1, 0, 0. Right, so this tells me that x2 is free and x1 has to be equal to negative x2. So the null space of this matrix right here is given by all the it's given by all things that look like x2 times the vector negative 1, 1, as I let x2 run through all the real numbers. And this, another way of writing this is the span of the vector negative 1, 1. So this is how we would have written it in Math 1B03, but we're going to write it as we do it in Math 2R. Really what this is telling me is that the eigenspace corresponding to the eigenvalue 5 is equal to the span of the vector negative 1 and 1. Okay, so hopefully that is kind of reminding you about some of the details. And I'm just going to skip the details for the eigenvector lambda equals 3. Maybe it's a good exercise that you try doing it yourself. And you would get span of negative 1 and 2. Okay, so the eigenspace of lambda equals 3 is given by the span of this vector. And this vector here and this vector here are the eigenvectors corresponding to this matrix. Okay, so we basically have enough stuff to diagonalize the matrix that we would do in Math 1B03. But I just want to make a couple points that we're actually can use this stuff to diagonalize the operator that we also started with, right, which is this operator here. Okay, and so the key thing here, and we'll see this in our next proof, is that we have two eigenvectors. They come from different eigenvalues, so they have to be linearly independent. Two linearly independent vectors in R2 is a basis. So R2 is the span of negative 1, 1 and the vector negative 1, 2. Okay, and more importantly, let's look what happens when we stick these vectors inside of my function, my operator t. When I plug in negative 1, 1, I get negative 5, 5, and that's the same thing as 5 times the vector I started with. But let's write it with respect to this basis, right? So I'll write it with respect to this basis. So I get this vector. And if I stick in negative 1, 2, I will get negative 3, 6. And that is the same thing in terms of my new basis is 0, negative 1, 1, plus 3, negative 1, 2. So if we were to use this basis and write the matrix of T with respect to this basis, what we end up with, oops, let me go back here. We end up with the matrix given by 5, 0, 0, 3. Okay, so remember we're using our new basis, right, which is negative 1, 1, and V2 is equal to negative 1, 2. Now, if you think back about how we did this in Math 1B03, we would have taken this matrix and we would have said that this is the diagonalization. And notice that right here, this is the eigenvector of 5, and this is the eigenvector of 3. So we actually are expressing things we're using the notation differently, but it's basically the same information. So in Math 1B03, you would have figured out this decomposition, and here are the eigenvalues. But really what you're doing is you're saying, oh, take the columns of this matrix P at the beginning. Those columns form a basis for your space. And if you take the linear, if you use that basis to if you use that basis to write the linear operator of the matrix you started with, you will get this diagonal matrix right here. Okay, so hopefully this connection, this example here, helps kind of understand a little bit about diagonalization and picking the right basis. Okay, and keep this example in mind when we come back after the break, when we ask the question, so when can you diagonalize? So you definitely can diagonalize. This example here shows you a diagonalization, but when can you diagonalize?